So I have to say, whoever organized the talks in this session has a really good sense for dramatic narrative, because we just heard about all of the leading models for explaining the phenomenology in these sources based on the first couple of years of data. And now I get to tell you about whether continued follow-up and monitoring of these sources, whether the models have withstood that. So, I should have started with an introduction. Yes, I'm Joheen. I'm a graduate student at MIT, working with Erin, Ricardo, Giovanni, Margarita, and many others. So I'm going to tell you about what we've learned from continuing to monitor these QPEs over the past few years since they've been discovered. As Ricardo showed you earlier, we have these 6 bona fide, confirmed QPEs, robust candidates, or robust QPEs. The original discovery source, GSN, one that was found from the X-ray archives, and then Ricardo basically cleaned up from there. So we didn't just find these and forget about them. These have been continued to be monitored in a series of already published and upcoming follow-up papers. So last year, Giovanni had a couple of papers on what GSN has done in the past years since it first started showing QPEs. So let me motivate the benefit of these long-term monitoring campaigns by recapping some of the prominent results from those. The QPEs were first discovered here in 2019 or so. And then over the course of a couple of years, the strength diminished quite dramatically. I mean, it's not a subtle effect. You can basically see it by eye. This was sometime in 2020, I think, and then the QPEs disappeared shortly thereafter. While that was happening, the underlying quiescence accretion disk was sort of decreasing in luminosity, and then eventually showed this long-term rebrightening during which there were no QPEs and the quiescent disk temperature increased. I mean, there's multiple ways you can interpret the second rebrightening. Maybe it's like a partial TDE of the same star that gave you the first one, or something similar to that. And all throughout the evolution of the QPEs in temperature and luminosity as they decreased, they continued to show this hysteresis cycle that was talked about earlier, or in other words, if you model them with a black body, this expanding emission region, and the value, this black body radius, even as the luminosities and temperatures changed pretty substantially, they conspired to change together in such a way that the black body radius was mostly preserved, mostly constant, about the radius of the sun, and expanding by a factor of a few over the course of the flare. Okay, I'll show more of that later. Okay, there was another paper last summer that Giovanni led again, which found that after the second partial TDE continued to decline, the QPEs reappeared, which was, quite a surprise, except with dramatically different properties, okay? There was quite a large deviation in their amplitudes. This one observation caught 2 of them right next to each other with like a sort of dramatic difference. And they seem to reappear at a different recurrence time, which is a big question for these orbiting Emery models. How do you suddenly change the orbital period or the collision times of this orbiting companion? So that's sort of an interesting piece of phenomenology. When they reappeared, and even in the bursts that were seen in the first series of observations, what was found was that, okay, so you can model both the quiescence and the QPEs themselves as black bodies. Well, the QPEs are black bodies and the quiescence looks like a disk black body. So if you compare the ratio of those temperatures, the amplitude of the QPEs in X-rays are going to scale with those. In other words, the QPEs stand out more when their temperature is significantly higher than the underlying accretion disk. And then when the underlying accretion disk heats up and gets brighter, in other words, as this ratio approaches 1, the QPEs become undetectable. So this isn't all that surprising, right? At all times that the QPEs are going on, the bolometric luminosity of the systems is basically dominated by the accretion disks, and the QPEs contribute maybe 10%. So it's like a real nice coincidence that basically our X-ray telescopes cut off at the right lower energy band, so that the QPEs really stand out in comparison because they're emitting at this higher temperature than the quiescence. And then finally, when the QPEs reappeared, we thought to make this plot of how does the peak luminosity scale with the temperature, because if it follows L bolometric luminosity goes like T to the 4, you infer basically a consistent black body radius, and that's like, very roughly seen, 2 within error bars, right? And what's interesting is that the 2 green points, which were from this observation over here, the first one after the QPEs reappeared, sort of seem to lie on this curve, reasonably well. So it's not just like you have these characteristic flare properties that are that change epoch by epoch. Even 2 that are separated by just tens of kiloseconds can lie dramatically on different parts of this curve, but still tend to follow it. Okay, great. So that was like a lightning recap of those 2 very dense papers that sort of found quite a lot of stuff. There's more coming for our XJ1301, and Ricardo's working on follow-up of ERO2. So most of this talk now is going to be focused on telling you about what we've done on ERO QPE1 in the past couple years since its discovery. So as multiple talks earlier have sort of alluded to, ERO QPE1 is this sort of notoriously difficult problem child of the QPE family, right? It's, Ricardo literally wrote a paper calling it the complex time and energy evolution. So it's much more poorly behaved or irregularly behaved than the other QPEs, in the sense that the very first observation in which its outbursts were detected showed what can be decomposed into these like overlapping bursts. And then, and again, if you look at the timing of the QPEs, right, many of them show this this well-behaved long, short recurrence, but attempting the same exercise for ERO1 sort of fails miserably, and there's quite a lot of unpredictable scatter in its recurrence time. So whatever is happening in these systems has to change a little bit to explain what's going on here. So long-term monitoring of this system basically found that it continued to surprise us in various ways. So we used, we led a multi-year NICER campaign on this source. So the first batch that was in Ricardo's original discovery paper came from August 2020, and we continued to monitor it over some years. You can see, there's more double flares detected there, and maybe you notice that the luminosity of the source or their energy output is sort of going down over time. So this is until October 2022. And then as we kept monitoring it from there, maybe we expected okay, they'll just keep going down until the flares become no longer detectable, but that's not quite what it did. You have this very irregular epoch where you have these really high amplitude bursts spaced by these sort of lower amplitude ones. The amplitudes maybe recover a little bit until they reach their sort of more typical pre-decline values here in January 2023, and then they sort of dramatically disappear in late last year. So something interesting is probably going on. And then, these are all with NICER light curves, which I'll talk about in a little bit, but NICER is not as sensitive as XMM Newton. So once we saw that the bursts disappeared in NICER, we checked with XMM to see whether they're still ongoing. And one flare was detected as recently as January of this year. So for all we know, the flares are still ongoing. But XMM observations are very expensive. So unless Norbert wants to give us, many, many orbits, because it costs basically a whole orbit to catch one of these flares, the monitoring program with NICER ends for now. So I'll talk briefly for the observers with an interest in NICER data analysis on some of the data analysis techniques that had to go into this, because even though NICER's response and rapid repeated observation capabilities are kind of amazingly well matched to the relevant timescales and energies of ERO1, NICER is not an imaging instrument, so you can't cleanly separate a source and background component as you can do with most other X-ray telescopes. Basically, when you point NICER at a target, all you get is these counts in a spectrum. You don't get any positional information on where they came from. But we do understand the spectral shape of QPEs fairly well. So even if we don't have spatial information, we can exploit the spectral information that we have and jointly fit the background of NICER, which is still something that we don't understand completely, but we have sort of a rapidly evolving understanding of. We jointly fit the background and source components, which gives us the source-only sort of black body component that's indicative of the QPEs. And here I've shown you sort of one of the easy detections that you wouldn't really have even needed this complicated source modeling for. But as the bursts get fainter and fainter, this basically becomes a necessity because they're only they're like barely peeking up over the background. So every single one of these points in light curves is a spectral fit, basically. So the light curves are incredibly expensive to produce, but once you've done that, you get spectral diagnostics basically for free for every single one of the points in this light curve. So I mean, this is fairly computationally expensive. It took me the better half of 2023 to construct these light curves, but then the rest of the analysis basically followed from there. Okay, so now that we have these amazing light curves and like 90-something QPEs from one source, which is, I think, more than all of the other ones combined, right? We can begin to test these Emory models that you just heard about for the past couple hours. So what are some of the predictions of the evolution of the QPEs that arise from these Emory plus TDE models? The first one, I mean, basically comes for free. It's in the name. We call them extreme mass ratio in spirals, right? So perhaps we see a long-term decrease of the orbital period over some time scale, maybe detectable, maybe not. A TDE disk is expected to cool over time. So if, as in GSN, we see that there's some sort of coupling between the QPE emission and the quiescent disk emission, perhaps we see that the QPEs also cool and become fainter along with the disk. The QPE emission in these models is powered by shocks. So that was sort of seen in this characteristic spectral hysteresis behavior from which we inferred that you have this expanding, cooling, emitting region. So maybe we see that being preserved over the epochs of observation, even as the luminosities and temperatures change. And finally, we have this prediction of you have like a dynamically complex system with a couple moving parts. You have your disk, you have your Emory, they can both precess. So maybe that will manifest somehow in systematic modulations of the timing in these QPEs. Okay, let's get started. So the plan here is basically just keep observing and see if we can test these. So the first one, again, the easiest. If the companion in spirals, the period should decrease. I mean, you can sort of see by eye that's not really happening, right? In fact, it maybe goes up a little bit. There's a ton of scatter, like I mentioned earlier in these bursts, right? Like even within a single epoch, like days apart from each other, they vary in recurrence time by up to like 30%. But there's this sort of overall secular drift over the couple of years, right? Corresponding to, I mean, yes, so corresponding to a delta P over delta T of, fraction of a day over nearly 1,000 days, so like 10 to the minus 4. This is pretty massive, right? Like gravitational waves, if you assume 10 to the 5.8 M-sun black hole and like a solar mass companion, like it should be of order like 10 to the minus 10 or something, right? And I mean, that should manifest in an in spiral. Gas drag can maybe do like a couple of orders of magnitude higher, but this is really like way, way higher than either of those effects will produce. So this is an interesting thing to explain. And then I'll talk a little bit about how one of the relevant factors that explain this could be precession of the secondary, because you have this sort of hierarchy of timescales that manifest in these systems, right? The Emory companion that's out at this orbit of 16 to 20 hours in this system, perhaps, is going to have a precession timescale of about 140 days due to apsidal precession. So just the orientation of this orbit is going to sort of rotate around. the black hole is presumably spinning, so there's going to be some lens-sparing frame dragging, which should manifest in nodal precession of the secondary on the time scale of, I mean, it's dependent on the black hole spin, but if you assume it's one a maximally spinning black hole, you get a minimum nodal precession time scale of 2,600 days. So just to show you, our observing campaign sort of traces over many, many apsidal precession periods of the companion, and some small fraction of the total nodal precession frequency. So maybe these changes are sort of dominated by the change in this period, and then if we look back again in 2027, they'll be back to here. But that's if the black hole is maximally spinning, which it's maybe not. So maybe we'll have to wait until like 2040 or something. Who knows? Okay, so that prediction is complicated. Okay, the TDE disk cools, prediction number 2. So do the QPEs become cooler or fainter? I mean, you could sort of read those off by eye, and in the XMM observation I showed you. So here I've plotted the peak luminosity of the QPEs over the various observing epochs. So this first and last point are the XMM observations. These are all nicer. This was our nicer upper limit. And you can sort of see that it's decreased by quite a dramatic factor. So about a factor of about 90. If you like, so these are those, they were peaking at about 10 to the 43 ergs per second and last about 10 to the 4 seconds. So the total inferred energy emitted by each of these bursts is around 10 to the 47 ergs, and then decreases to some fraction of that. Do the QPEs cool alongside that? So here I've shown the characteristic temperatures of the QPEs in these colored points, plotted over the gray contours show the QPE evolution themselves for some of the epochs. And the main punchline of this slide is that they cool by about a factor of 3 from our first XMM observation in 2020 to the last XMM observation a couple months ago. And the astute among you will notice maybe 3 to the 4 is about 90 to astronomers, right? So maybe the black body radius that we infer is being preserved somehow. And if I plot this, this brings us to the next prediction for shock-powered emission. Perhaps we see that there's a similar sort of expansion in the black body emitting radius over the various epochs. So this is essentially the same thing that I plotted for the temperature evolution. You have your QPEs underplotted, I guess, in light gray, and then the inferred black body radius of each QPE all plotted on top of each other. So again, this is about the radius of the sun, expands by a factor of a couple, and you see maybe this evolution changes a little bit, right, over the various epochs. But it never changes by a factor of that much, right? It doesn't change by a factor of 3, and it certainly doesn't change by a factor of 90, right? So it's roughly preserved, and you always sort of see this expanding behavior over the courses of the flares. And I mean, it's sort of an amazing coincidence. I don't really think it's a coincidence. But if you compare to GSN 069, I mean, even in these two sources where the behavior is so dramatically different, you see again the black body radius is about the radius of the sun. And actually the same also goes for RxJ1301. Again, a few times 10 to the 10 centimeters. So whatever is producing the flares in these systems likes to start at about a solar radius. One natural question you could ask when you have this expanding emitting region is the expansion adiabatic, right? Does it follow PV to the gamma equals constant? So for a gamma of about 4/3, what I've done here is, if the orange basically just plots the median trajectories. So if I clear away all the junk, you can see sort of, so the tracks start in the epoch where the temperature peaks. And at least a couple of these, the expansion rate follows what you infer from the temperature evolution to be adiabatic quite closely before basically departing. You see that here as well, but not quite here, right? So So you have maybe something that looks like an adiabatically expanding region, which then drops off and the expansion becomes sub-adiabatic. Maybe, I mean, at some point the expanding cloud is going to become optically thin, so the photons can no longer efficiently do PDV work, but that's more speculation. So this is an interesting trend I actually want to look more into and would be happy to chat about. Okay, and the final prediction that I had laid out earlier is that maybe you see the manifestations of disk and emery precession in these systems. So in GSN and Euro 2, you see this sort of nice, remarkable, long, short, alternating behavior, right? But this doesn't really work for Euro QPE1. If you attempt to fold the odd and even bursts, you see this really high scatter. So the clock in this system is relatively more irregular. And maybe what we thought to check with this with these many flares was if there is any evidence for a super period that's systematically modulating the timing of these flares on some period slightly longer than the QPEs. And the reason we can sort of do this is because there's this nice hierarchy of timescales, right? The emery precesses on a much longer timescale than any of our observing epochs. So perhaps we can look for the effects of the disk nodal precession on the timescale of one of the observing epochs. And indeed, what we find if you sort of take the amount that your QPEs are delayed or advanced with respect to a fixed period, is that there's this almost sort of sinusoidal-looking modulation over the course of each of the dozen or so flares that are seen in any of the 1 to 2 week observing campaigns, with a characteristic period of around 6 days, a little under 6 days. But I have to give the caveat that this isn't seen in every epoch. So these are all of those shown here, right? You see it clearly in some, not very clearly in other. And this is a really interesting one. It sort of briefly showed this long short behavior for one epoch. Who knows what's going on there, right? I have ideas, but we can chat later. And a fun consequence of this, okay, I'll try to finish up quickly. But a fun consequence of this, right, is if you take this to be the disk nodal precession frequency, right? So for half of the lens-staring cycle, the disk is running away from the orbit, and then the other half it's running towards the orbit. You can sort of get constraints on the black hole spin that are very degenerate for what you assume about the disk. Okay, the disk, outer truncation radius and the disk surface density profile. But this is sort of a fun exercise to think about. And okay, so this slide was just some of my rampant speculation about what might be some of the explanations for all of the irregularity in Euro QPE1, but I can see Brian standing here menacingly, so maybe somebody ask me about this and I'll talk about it later. Yeah, okay, so I'll leave you with my summary slides and then, yeah, happy to take questions, thanks.
So I'll use my prerogative to this question yet again. So going back to this cooling of the QPE emission and the quiescent emission,
yeah,
just to make a point that that the emission temperature in these collision models is very sensitive to the disk density, and if these disks are undergoing changes in that density at the collision point due to partial TDEs or limit cycles, as we studied with Itai, you could imagine that flare temperature is changing and may become unobservably soft in many cases. Mm-hmm. So my question is, could this be a selection effect that we only see QPEs when they're harder than the quiescent emission, and when they're not, we don't see them at all? So as the quiescent emission cools, we are preferentially seeing cooler QPEs. I guess this would predict that the limit cycle, I don't know if it would predict this for sure, but maybe the limit cycle over which you see QPEs is growing as well. I mean, anyways, I guess I'm asking is, could this be a selection effect?
Yeah, so then maybe eventually these start to cool into
as you cool, you can see softer QPEs basically that you wouldn't have been able to see when the disk was hotter.
Oh, sure. Yeah, but I guess that's sort of a difficult question to answer with only the X-ray telescopes, right? I mean, these are already at the very lower limits of what the X-ray telescope bandpasses cover. So I think really what you would want is like a UV instrument to start to see these, right? Or,
so you don't see the, sorry, I must have missed, so you don't see the quiescent flux for this?
no.
Okay,
So,
sorry.
yeah, so the quiescent flux is never detected by NICER in this system, and it's
Okay.
like marginally detected.
So
by
you don't
XMM.
know whether the, but if, yeah, okay.
Yeah. Well, in the 1 sigma detections of XMM, we actually do find, okay, yeah, these are shown in table form, but the quiescence goes from, yeah, so this is the first epoch in 2020, so around 130 to about 80 keV. But yeah, that's with very few counts. Yeah.
Right, and so, yeah, okay, very good,
Yeah.
thanks. Another question over here.
Yeah, Joheen, this is fantastic work. I did have one question. You mentioned your analysis of the periods and also the amplitudes.
Sure.
But I did see an appearance, and the super periods, but I did see the appearance of differences in the actual line, the light curve eruption shapes, in that there seemed to be very slow rise times in a few cases, and then very sharp rise times, and then the decay. So I was just curious to what degree you've actually looked at the shapes of individual peaks and how they might correlate with the other properties.
Yeah, sure. So, I mean, I fit all of these with an exponential rise and decay model. This is what, we did for the XMM bursts. So we assumed that this would be a nice description of all of the QPEs in this system. I mean, we looked quite closely at whether the rise and decay times or even the, delay between the bursts correlates with any of the other properties in these QPEs. And there aren't really any apparent correlations like that. So that's sort of interesting. The timing modulations were done by using the peak times of each of these. So those are fairly well constrained in most cases, right? You can sort of see the error bars are quite small, except in some of these where the data is a little more sparse. But yeah.
I was just wondering if people have a theoretical understanding as to why the rise times are so varied.
Yeah, I don't think so. But
Yeah,
I mean,
some are so sharp, and then the others almost look symmetric with the decay.
Yeah, it's interesting.
Yeah. I mean, I guess I would say if really there is some precession, obviously the inclination, how much material you're ejecting might change, but yeah, unclear. Questions, comments? Okay, if not, let's thank him again. Cool. And we have